If the interval of integration AB is in some sense small, then Simpson's rule with n equals 2 subintervals will provide an adequate approximation to the exact integral. By small, what we really mean is that the function of being integrated is relatively smooth over the interval AB. For such a function, a smooth quadratic interpolant like the one used in Simpson's rule will give good results. However, it is often the case that the function we are trying to integrate is not smooth over the interval. Typically, this means that either the function is highly oscillatory or it lacks derivatives at certain points. In these cases, Simpson's rule may give poor results. One common way of handling this problem is by breaking up the interval AB into small subintervals greater than 2. Simpson's rule is then applied to each subinterval, with the results being summed to produce an approximation for the integral over the entire interval. This sort of approach is termed as the composite Simpson's rule. Suppose that the interval AB is split up into n subintervals with n an even number. Then the composite Simpson's rule is given by the integral of function x dx from a to b is approximately equal to h over 3 multiplied by the summation of f of x sub 2j minus 2 plus 4 f of x sub 2j minus 1 plus f of x sub n, where j is from 1 to n over 2. The value of j is from 0, 1, and up to n minus 1 and n. With h equal to b minus a all over n, in particular x sub 0 equals to a and x sub n equals b. Expanding this formula, we have h over 3 multiplied by f of x sub 0 plus 2 times the summation of f of x sub 2j, where j is from 1 to n over 2 minus 1, plus 4 times the summation of f of x sub 2j minus 1, where j is from 1 to n over 2, plus f of x sub n. Simplifying this formula, we'll have the integral of f of x dx from a to b is approximately equal to h over 3 multiplied by y sub 0 plus 2 times y sub 2 plus y sub 4 and so on up to y sub n minus 2 plus 4 times y sub 1 plus y sub 3 and so on up to y sub n minus 1 and plus y sub n. Let's take a look at this example. Evaluate the integral of square root of 5x plus 4 over x squared dx from 1 to 6 using 8 subintervals. Solving for h, we'll have 6 minus 1, which is 5, divided by 8 equals 0.625. Next, we will solve the value of the function using the different values of x. Forming our table of values using the solved value of h, we'll have plugging the values we got from our table to the derived formula, we'll have therefore, the integral of square root of 5x plus 4 over x squared dx from 1 to 6 using 8 subintervals is 23.790137. Now solving for the error committed using the composite Simpson's rule, we have the approximated value minus the true value all over the true value times 100. We have here the true value of the integral and then the approximated value using the composite Simpson's rule. Plugging those in our formula, we'll have 0.162562431%, which is a small difference. And that's it, guys. I hope you've learned from this discussion, and thank you.